Hi, welcome to Computer Systems 214. Today we're looking at Lecture 11. As you can see, it's called Multiplexers. But to be honest with you, I would prefer to call this Shannon's expansion theorem. Now I am 100% a geek, and that's why this is one of my favorite lectures in this module. It's where we apply something called Shannon's expansion theorem to implement logic circuits using only multiplexers. Before we get there, let's have a quick recap of what a multiplexer is. As you can see on the screen here, 2x1 multiplexer is shown. This 2x1 multiplexer has two inputs. That's data channels, one of which will be connected to Y, and then a select line which controls, and that's why it's called a control signal, which controls which one of these two will be selected. So D0 will be put onto Y if S is equal to 0, and if S is equal to 1, then D1 will be passed through onto Y. And that's the logic truth table for it. So that's a multiplexer, or like we said last time, the short way of saying multiplexer is just mux, or the plural being muxes. Now, we've only done 2-to-1 multiplexers, but obviously you can do more than 2 input multiplexers. And on the screen there you can see there's a 4-channel input, 4-input multiplexer. If you have 4 inputs going from D0 to D3, you obviously have to use more than one select line. So in this case we're using 2 select lines, and those 2 select lines correspond to each one of those inputs. If the binary value of S1 is 0, if you consider those as 2 bits, the binary value is 0, 0, it'll select channel 0. If the binary value is 0, 1, it'll select channel 1. If it's 1, 0, like 2, it'll select 2, and if it's 1, 1, it'll select 3. So by manipulating these 2 data bits, we select one of the inputs which is connected onto Y. Now, the more generic term to do this is to say an n-to-1 multiplexer needs log 2n select lines, or easier way to put it, it's a 2-to-1 multiplexer needs 2 data inputs and therefore 1 select input. 8-to-1 needs 8 data inputs, 1 data output, and 3 select lines. Then a 2 to the n multiplexer requires 2 to the n data inputs here, 1 data output obviously because it's multiplexing, and then n select lines over here. So just keep that in mind as we go through, but multiplexers are, like I said last time, pretty common. Now a multiplexer, a 4-to-1 multiplexer can be built using either AND gates and an OR gate, or it can be built using a multiple of 2-to-1 multiplexers. Now before we go on, let me just say we're doing this for a reason. Okay, the next 4 or 5 slides or so, it's going to seem weird and spurious, but it leads into Shannon's expansion theorem. So we're going to show you a few weird quirks about multiplexers and logic gates, and then we'll be formalizing the structure of going from Boolean algebra into multiplexers rather than into AND gates. So just stick with me and follow these weird examples and try to follow how they work, and then I'll tell you why they work. Okay, so the 4-to-1 multiplexer that I've got on the slide here, you can see there's data 0, data 1, data 2, and data 3, and each one of these AND gates just acts like an exclusive activation gate. Let me explain what I mean by that. The NOT of S1 and the NOT of S0 goes into this gate. The only way that A1 can pass through here is if all of those are 1. If that is a 0 and that is a 0, this will be 0. The only way for it to be a 1 is that must be a 1, that must be a 1, and this must be a 1. If this is a 1 and this is a 1 and this is a 0, the output will be 0. Conversely, this gate enables the passage of D0 by having those two input pins made high. I'll say that again because it's really important. This AND gate essentially allows D0 to pass through if that's a 1 and that's a 1. Because if that's a 1, that's a 1, and that's a 0, there'll be 0. If that's a 1 and that's a 1 and that's a 1, that'll be 1. So it essentially mimics just a normal buffer if those two pins are high. In the same way, in other words, if those two are low, then those two will be high. In other words, to select D0 to appear at that point there, both of those need to be 0. Let's just look at the next gate. The same thing happens at the next gate, except it doesn't use the NOT of S0, it just uses S0, and it uses the NOT of S1. So if S1 is 0 and S0 is 1, then we have a 1 here and a 1 here, which means that whatever comes out here will reflect D1. So this AND gate acts like a passage for D1 in the scenario where S0 is equal to 1 and S1 is equal to 0. So essentially these two are selecting which one of these AND gates are going to be active, or which one of the AND gates are going to allow its data bit to go through. So we're not abusing, we're using the property of AND gates to select one of the data pins. As you can see, just a final one here, if S0 is 1 and S1 is 1, then what will happen is this AND gate will say, if this is 0, I will present a 0. If this is 1, I'll present a 1. So it acts like an activation, if you want. And then what happens is these are all ORed, and this is important to understand, so just bear with me one more step. Because of the way we've connected the select lines, you'll agree only one AND gate will be active at any given instance, because this requires a 0, 0. This, when I say 0, 0, I mean at the inputs. This requires a 0, 1. This requires a 1, 0. This requires a 1, 1. So logically speaking, only one of these gates will be enabled at any given time, which means this OR gate will take through only one of those. 3 of them will be 0, guaranteed. The other one will be passing through the data bit, and then this OR gate will just be passing through the data bit. So because of the way that we've set this up, this OR gate just says passing through one of them, because all the other ones will be 0. Okay, hopefully that makes sense to you, because that's the way an OR gate works. If any one of the inputs is 1, it gives a 1, otherwise it gives a 0. And because 3 of the inputs will be 0, the one that's not 0 will be passed through. And if that one is also 0, the 0 will be passed through. So this essentially mimics a 4-input multiplexer. Now try to forget about this for a second. On the right-hand side here, we have another implementation of a 4-to-1 multiplexer. What you can do is you can cascade these or build a tree of multiplexers. So this channel, if you want, this block of multiplexers, it selects between either that one, or then that one and that one. So what is not shown here, which is implied, let me draw it actually, is that that is connected to S0. So if you're wondering what's going on here, it's not anything funny, it's just S0 is connected there. Okay, that's all that's going on. So anyway, if S0 is 0, then that will be selected there, and that will be selected there. And then if S1 is 0, it'll select this one. If S1 is 1, it'll select this one. So in effect, it has this multiple stages of selecting, mimicking a 4-input multiplexer. Let's just do one more example. If S1 is 1 and S0 is 1, so S0 is 1 and S1 is 1, then this one will select this channel. This selection will select that channel and that channel. So this will appear here, that will appear here, and then this one will select this. So what comes out is D3. So for condition 1, 1, the output is equal to D3. Let's do just another one in case I've lost you. Let's just wipe this real quick. If I've got the condition 0, 0, this is 0, this is 0, then because this is 0, D0 is manifested here. Because this is 0, D2 is manifested here. And because this is 0, this one is selected. So what comes out is D0. And you can do the same with the other opportunities there, or the other cases. So in effect, we've built a multiplexer, a 4-to-1 multiplexer, using two initial stage 2-to-1 multiplexers and another final stage 2-to-1 multiplexer. Okay, good. You can also expand this, so you can make a 16-to-1 multiplexer, which is shown on the board there. And all you do is just combine more of these together. So then you take a 4-to-1 multiplexer, as is shown here, and another 4-to-1, and another 4-to-1, and another 4-to-1, and in this side here, you then select another 4-to-1. So let's just do one example. If that's a 0 and that's a 0, this channel will be selected, that channel will be selected, that channel will be selected, this channel will be selected here, and then because these two are zeros as well, that channel will pass through. So W0 will be put out if the two input conditions are 0. A 4-to-1 multiplexer being used, or many of them being used as a 16-to-1 multiplexer. So your multiplexer can also be used as a lookup table to implement logic functions. So what that means, if you don't know what a lookup table means, in software typically use a lookup table where you provide some input conditions into a function, and this function has a lookup table that looks up the value relative to the two input conditions. And that's essentially what a multiplexer does. So what you can say for a multiplexer, a 4-to-1 multiplexer, is I want you to behave like an AND gate. So I'm going to give the two inputs on this side here as my two select lines. And then on the inputs of this multiplexer, I just connect a 0, a 0, a 0. That's what this signal ground is for. And over here, I think that's supposed to be 5 volt. It's a bit of a horrible drawing there. That is connected to 1, which means Y is essentially doing an AND of A and B. So this multiplexer is now strangely doing an AND function. If you think about it a bit more, you will probably figure out that you can do this using a 2-to-1 multiplexer. So let's look at the next slide of how to do that. You can do an AND function. I'll get back to that in a second, the rest, but you can do an AND function in the following way. So one of the two inputs sits there, the other one sits here, this is connected to ground, and if you just think about the truth table real quick, let's just check it real quick actually. Let's do a sanity check. We do perfect induction on it. 0, 0, 0, 1, 1, 0, 1, 1. What comes out? If A and B is 0, so this is 0, it'll select the ground to Y, so I don't need to check further. 0. Again, the same case here. If A is 0, it'll just select that ground, so that's 0. And then if A is 1, it'll select B as an input, and that's interesting. It'll just select B, so there'll be 0 and 1. So in what's just happened, there's some hidden logic. So let's work back to the beginning of the slide now. Don't know if you realize this, but essentially what we did was we said, try to follow this. Let's group my inputs. Let's group them into groups where A is 0 and where A is 1. If I've captured them as groups, I ask myself, how does the output relate to the remaining input? And the answer is clear. If A is 0, then Y is just equal to 0. There's no relationship with B. So Y is just always 0. if A is 1, this looks the same as B. So I'm just going to say that again. We group the inputs according to some grouping that we choose. But for example, this group was, let's look at all the cases where A is 0 and all the cases where A is 1. Then we consider what is the output relative to the remaining inputs. So the output here, no relationship, just 0. And the other one, it's exactly the same as B. So that's why we have a 0 connected in this case. So if A is 0, we use a 0. That's what this means. And if A is 1, we use B. That's what this means. So this is where we're leading into now. We're leading into Shannon's theorem. I can hear him calling. Okay. Same thing for an XOR. So for an XOR, again, we've made this grouping. We've said, let's take a group where A is 0. Let's consider what Y is. Y is exactly equal to B. That's why we connect B here. If A is equal to 1, what is Y equal to? Oh, that looks like the inverse of B. So the inverse of B will be passed on to Y if A is equal to 1. So there we go. We've just made an XOR gate using a mux. And here we've made an AND gate using a mux. And here we've also made an AND gate using a mux. Okay, now we get to a bit more detailed one. Now the question is, how do you do a 3-input XOR gate using a multiplexer? Now remember what I said, the next few slides are going to be a bit intuitive and kind of random. I think that's the way the millennials describe it. I don't know what you guys are. But we're leading into the theory, so just stick with me. So what they've done here, one method to do this is to ask yourself, okay, if we make groups of input conditions, what will happen with the output relative to the remaining input conditions? So what we've done is we've split this up into 2 blocks. Again, one where W1 is equal to 0. Again, one where W1 is equal to 1. Just looking ahead a bit, we will use that W1 as the multiplexer to select between 2 inputs. Okay, so we're essentially scrapping this line here and saying we will represent it with a multiplexer. We'll choose. We'll select which one of the functions we want to use based on what W1 is. Okay, now we've done that. Now you need to consider, what does this look like? So if I can just, actually let me just hide this for a second. So forget about this. Let's just consider this block here. This block here looks very much like an XOR. For the 0, 0 condition, 0. For the 1, 1 condition, 0. For the condition where you have the 2 separate inputs differing, then the output is 1. So that's an XOR. So you could have just stuck an XOR gate here if you had one. But we don't. So what we can do, on the previous slide, we determined an XOR is made by one selecting and the other one being direct feed and inverted feed. So let's use that. So if you want to implement an XOR, we're saying for this input condition here, we want to make an XOR, and that's what this is. Just one of the variables selecting and the other variable going in directly, and the inverse of it going into the second selection. That's all that's going on. It's exactly the same as that. So now we've made the top half. We've done that bit. So this will already behave properly if W1 is equal to 0. Let's look at W1 is equal to 1. If W1 is equal to 1, it's this block. What happens to the rest of the inputs, or how do the rest of the inputs affect the output? Just looking at this, you can see that's a negative XOR. Now, doing a negative XOR is pretty simple. We already have the XOR, so we just invert it, and Bob's your uncle. Or Bettina's your auntie. Okay, yeah, so that is simple. We've made a 3-input XOR using multiplexers. Now again, we're just building towards Shannon, so bear with me. In this example, we've used 2-to-1 multiplexers. We used 2-to-1 multiplexers, and therefore we eliminated only one variable in the beginning. So that'll make sense in a second, but keep that in mind. Because we used 2-to-1 variables, we eliminated one variable. Then we get on to the example where we do 4-to-1 multiplexer. Now, for a 4-to-1, immediately you should think to yourself, for a 4-to-1, I have 2 select lines. So rather than eliminate just 1 column, let's eliminate 2 columns. So what we're going to do is we're going to say, let's group them into separate groups. The first group, I'm just going to highlight this actually, the first group is where W1, W2 is 0, 0. The next group is where it's 0, 1. The next group is where it's 1, 0, and the next one is where it's 1, 1. Now you need to keep your wits about you. Obviously now it depends on when you connect these, if this is the least significant bit or the most significant bit, right? Because that's going to make a difference. And the textbook, unfortunately, is not consistent because some of these examples are from a different textbook. Okay. Yes, so we've got these groups now. And now all we need to do is we need to link this group. We need to link to this line. This group, we need to link to that line, and this line. And unfortunately, in this example, it doesn't matter if you have the order of these two wrong because they've chosen a symmetrical output. So as I say, just keep your wits about you, whether this one is connected to select 0 and select 1, or whether it's select 0 and select 1. Otherwise, it's going to be a mess. But let's stick with this example for now. Okay, so for this block, you ask yourself, the remaining input, how does that relate to the output? As you can see, W3 is just equal to F, or F is equal to W3. In this case, you can see it's just the inverse. In this case, you can see it's again just the inverse, and in this case, it's W3 again. So how simple is that? A very simple multiplexer, which selects between 4 inputs, and these 4 inputs are just W3, W3 for the 2 extremities, this one and this one, and then the invert of it for the middle 2. That's nice. Okay, so now, as I said, just going back real quick, we did a 4-to-1 multiplexer. We had to eliminate 2 columns there. Right, we can also do a 3-input majority function. I don't know if you know what this function does, but it checks how many inputs are equal to 1, and if at least half of the inputs are equal to 1, the output is equal to 1 as well. So let's look at how to implement this with a multiplexer, and we're using a 2-to-1 multiplexer. Because we're using a 2-to-1 multiplexer, by the way, I'm not saying this because I'm stupid, I'm saying it because I want to drill it in. Because we're using a 2-to-1 multiplexer, we need to eliminate 1 column. The 1 column that we eliminate is W1. Because we eliminate W1, we need to make groups of where W1 is equal to 0 and a group where W1 is equal to 1. So in this group, you have to ask yourself, what does F look like relative to the other inputs? So if you just consider this grouping here, there we go, that looks surprisingly like an AND gate. Would you agree? So F is just equal to the AND of those two. If you were to consider the second group, those there, what does that look like? That looks surprisingly like an OR gate. So that's what this is, an OR gate. So you can combine these now. If you want to use a multiplexer and logic gates, what do? We select that multiplexer, and the AND gate is the first bit, and the OR gate is the second bit. Right. I hope you're falling in love with multiplexers yet. Okay, so now the next question is, how do you do this 3-input majority function with a 2 multiplexer from the mathematical equation? So now we're going to do it with math, and now it's starting to lead a bit more deeply into Shannon's domain. So if we were to express this mathematically, and with this I mean this truth table. So if you were to take this truth table and just do the sum of products, so we did what we do normally, and we consider which ones are 1, and then write each one of their min terms. Then this is what it will look like. F is equal to 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1. And that's really what those there are, those ones. Then if you were to manipulate this mathematically, you can take W1, you can take out here as a common variable, take it over there. What remains is basically that. And this is what's written here. And then, if you look at this carefully, you'll see we've built a mux. By doing that, we have a term. What was it called again? Collateral damage or something. Implicant. The implicant here, you can see, has a not W1 here and a W1 here. So effectively, this is multiplexing. This is saying I'm selecting these two if W1 is 0. I'm selecting this massive block here if W1 is 1. So by just doing that, writing it in the form where I have a not W1 with a few terms or a term, and W1 with a few terms or a term, I'm essentially doing a multiplexer. I hope you can see that. If you don't worry, we'll get there. Okay, the next step, that's again very non-intuitive. We expand this. We duplicate this term, write it out twice. And this is part of the formal structure of Shannon, so don't get a fright. So we write this out twice. By doing that, we can break up this function even further by then again taking out W2. Sorry, they've taken out they've not taken out anything. So now they expand these, actually, so for the next step, we can now expand this and just write it out twice so that we can take out W3 from the first two terms and W2 from the next two terms. And because those become a 1 and those become a 1, what we're left with is just W1's inverse, selecting a term, W1's normal literal, or true literal, selecting another term, which is a multiplexer. So just look at this. This is the AND of W2 and W3. This is the OR of W2 and W3. Look back at that. That's exactly what we got here. So this was like an intuitive derivation. We just used logic. In this case, we used Boolean algebra. So I don't know about you, but I find that fascinating. All right, so let's look at a 3-input majority function with a 4-to-1 multiplexer this time. So immediately light should go off. The examiner or whoever asked for a 4-to-1 mux. 4-to-1 mux has 2 select lines. Because it has 2 select lines, we're going to have to take out both of those columns. Because we're taking out both of those columns, we need to make groups of those two. So things that look the same from those two columns, like that and that. So it's a 0-0 group, a 0-1 group, a 1-0 group, and a 1-1 group. Again, the textbook chose to go symmetrical on the inputs, so it doesn't matter which order these two go, but obviously you need to pay attention to that when you make your own multiplexers. Okay, so now we need to ask ourselves, for this group, how does the remaining input relate to the output? It doesn't, it's just 0. For the next one, how does it relate? Oh, it's exactly equal. The 0 and the 1, and a 0 and 1, so it's just equal to 3. F is equal to 3, W3. The next one, it's also exactly the same. So when that's the input condition, the output is just equal to W3. And finally, the 1-1 condition, the 1-1 condition, in that case, the output is always equal to 1. So when we make this multiplexer, we're going to say it's a 0 for the 0-0 condition, it's a 1 for the 1-1 condition, and for the two middle conditions, it's just equal to W3. So that's a 3-input majority function implemented using a multiplexer. Hope you're still following this. Any questions? Okay, I'll take that as a no. Now we get to the crux. This is Shannon's expansion theorem. Now, Shannon's expansion theorem basically formalizes the weird things we've seen in the previous slides. It says any Boolean function that has a certain number of input variables can be written in a multiplexer form. It can be written in a form that says f, whatever was the input condition, is equal to not one of the variables. Let's just make it W1 in this case. Needn't be one of the variables. And it, so the product with f, and this is important to get, so listen up carefully, and it with f such that in f we replace every instance of this variable with 0. So we take W1 out, and every time where W1 occurred, we replace it with 0, or with W1, and now we take W1 out, and it's ANDed with F, and then everywhere where W1 occurred in that function, we replace it with a 1. Another way to write it is just F is equal to the not of one of the variables times what is called the cofactor of F with respect to W1's inverse, plus with W1 times, or product, the cofactor of F with respect to W1. But essentially it's just saying any function can be written as a multiplexer, and all you do is you, for the 0 condition, you write out the whole function and you replace all the instances of that variable with 0, plus, so ORed with the true form of that literal, and it with the function again, you write out the whole function, and now you replace all the W1s or whatever that variable was with 1s. That's just amazing. And that basically gives us a tool with which we can then implement multiplexers using or directly from the mathematical or the algebraic equation. So let's look at an example. Again, the important part is to understand that you need to think about whether it's a 2-to-1 or a 4-to-1 multiplexer. So always remember this. So in the exam, we'll say 2-to-1 multiplexer, do this with Shannon's expansion theorem. So this is the function that we want to do. It's not W1, not W3, plus W1, W2, plus W1, W3. And the question says, use a 2-to-1 multiplexer. How do we do this? Okay, so you choose which variable to take out, as it were, so to develop or extract. In the exam, we'd probably tell you which one to use. No guarantees though, just makes our lives easier because it marks easier. But in this case, they've extracted W1. So first, they've written not W1, and it with the cofactor, the whole function, replacing W1s with 0. So let's just look at how that really looks. So if you take this whole thing here and you rewrite it, but every time you had W1, you replace it with 0, then this turns into a 1, this turns into a 0, and this turns into a 0, and that's what's going on here. So there's a 1 here, a 0 here, and a 0 here. So we've rewritten the cofactor for the not of W1. Then you expand the whole thing again. So you take out W1 in this case, and now we're saying if you replace those values, just wipe this real quick. If you replace all the instances of W1 with 1s now, that turns into a 0 because it's not W1. That turns into a 1. That turns into a 1, which means you have that 0 going there, that 1 going there, and that 1 going here. Now, if you put that into the equation, the 1 and anything just becomes that anything. 0 and anything is killed. 0 and anything is killed. 0 and anything is killed. 1 and something goes there. 1 and W3 goes there. And voila. And that's it. So if you have to draw this out, then you've got the multiplexer, 0 and a 1 selecting between either not W3 or W2 or W3 going in there. Now, it's important to note this example only uses one multiplexer, and then suddenly it has the capability to pluck OR gates out of the sky. In the exam, we'll expect you to also take this into an OR gate. We'll be happy with you using inverters, but we'll probably tell you to just use muxes, nothing else, just multiplexers. So then you have to take this one and use a multiplexer to develop that function as well. Now let's do exactly the same thing, but this time we use a 4-to-1 multiplexer. Now because we use a 4-to-1 multiplexer, we're going to have to go into different stages. We'll first do the one variable and then the other variable. That's one way to do it. Or you can take out two at a time. So Shannon's expansion theorem still works if you take two variables at a time. So here we've taken out, and you should be able to see this is the binary condition 0, 0, the binary condition 0, 1, binary 1, 0, binary 1, 1. And when we took them out, we replaced them with 0, 0, or with 0, 1, or with 1, 0, or with 1, 1. And every time we write out the whole function, that whole thing, and you just replace it with 0, 0, or 0, 1, or 1, 0, or 1, 1. If you do that, you will find, let's just do one of them, the 0, 0 condition. So this will turn, we're taking out W1 and W2. So this turns into a 1. That stays W3 because we haven't taken it out. W1, W2 will change into 0, 0 because they're both 0. And then W1, W3 will turn into a 0, W3, so that also changes into a 0. That's just for the 0 condition. We do the same for 0, 1, same for 1, 0, and same for 1, 1 here, here, and here. When you've done that, you then complete the logic, so just check. So this turns into just W3. This killed. This turns into not W3. This here turns into 0. This turns into 0, and that turns into W3. And then finally, the last one, that's a 0. That's a 1 ORed with that. Because it's a 1 ORed with something, it's just 1. So here we now have a 4-to-1 multiplexer. This is the first select option, second select option, third and fourth. And each one of them has a singular input going into the multiplexer. So if you had to draw this out, this is what you'll have. W2 and W1 selecting between all these input conditions. Now the book has finally trapped itself. It's gone into a position where it's not a symmetrical input anymore. So let's just check what they've done. So the normal W3 condition is the third one. So normally you would expect this to be 1, 0, 0, 0, 0, 1, 1, 1 conditions. And this happens when it is 0, 1. So this is actually the 0, 1 condition. So this is the most significant bit. I hope that made sense. So basically, this one here is supposed to be selected when... oh, sorry, I'm wrong. I'm wrong. Sorry, this is actually the 1, 0 condition. So 1, 0 is this condition. So the way that the textbook has done this is the MSB and this is the LSB. So what I would hope to tell you in the exam is that these two are connected to, let's say, S1 and S0, so that you know which one is the most significant, right? So that you can see, hey, this one is connected to the most significant, this is to the least significant. But in general, the left-hand side one is the more significant and the right one is the least significant. But unfortunately, the textbook kind of swings around between using inputs as W2 being most significant or W1 being most significant. Anyway, I hope you got that. I hope I didn't confuse you now. If I did, don't call me, I'll call you. Okay, so that brings us to the second last example that we have from this lecture. In this case, we want to use a 3-input majority function, and we want to implement it using only 2-to-1 multiplexers. So we only have 2-to-1 multiplexers, which means we're going to extract one variable. So this is the 3-input majority function written down here in an optimized form. And what we can do now is to take out one variable. In this case, we're taking out W1. And because we're taking out W1, if we rewrite this, the first is the not case. So we're replacing all the W1s with zeros. Therefore, this becomes 0. This becomes 0. And this is unaffected, so that just passes through. Next, we take out W1, not the invert, and then we replace all the W1s with 1, 1. So that's why we have a 1 and a 1 here. Now, cancelling out, anything ANDed with 0 is 0, anything ANDed with 0 is 0, and then those two, if you add and them together, it's just that. So all that's left is that. The next one, 1 and W2 is just equal to W2, 1 and W3 is equal to W3, and then this just stays there unaffected. Right, so now all you have to do is just, this also reduces further, so if you just take out W2 there, it's 1 plus W3 plus W3, which means this turns into a 1, so all you're left with is W2 plus W3. Okay, so now the question is what now? We've reached this point. Now if you had logic gates, you could easily just use this 2-to-1 multiplexer and then use an AND gate and an OR gate. But we do not. We've told you to only use multiplexers. So what do? Well, the simple thing is you just say, let's make this equal to G. Let's make this equal to H. And therefore, we can use Shannon's expansion theorem on G and H. So just keep your wits about you when you do this, because typically this is where you make mistakes. G is equal to, and then we take out one of the variables. In this case, we're doing W2. The inverse of W2 means that this here turns into a 0. That there goes down, but you can see this whole thing will turn into 0. And then if we replace W2 into it, as a 1, then it becomes a 1 here. So what is left is W3. So this is a multiplexer in itself that uses W2 to select between 0 and W3. The H, which we said is going to be this one, that will just expand a bit further. In that we take our W2, we replace, because it's the inverse, we'll replace this with a 0, so that's why we have 0 here. Plus W3, which is unaffected by W2. And then again, if we take out the W2 and replace with 1s, we get 1 plus W3. Right, the W3 again, just unaffected. So anything plus 0 is just that, anything. And anything plus 1 is just a 1. So what we end up with, and just pay attention, many people for some reason don't get this. This is a multiplexer. I'm just going to draw it actually. It's also on the next slide, I believe. But this is a multiplexer which chooses W1 to select. What does it select? It selects either W2 or W3. You can actually write it here if you want. Yeah, that makes it a bit easier. And this selects W2 plus W3. But the question is, how do we get that? So W2, W3, we can derive using a multiplexer. This multiplexer must select using W2. So another multiplexer. It uses W2 to select, and at its input it has a 0 or it has a W3. Same here, a multiplexer, and this multiplexer will select using W2. So W2, and it selects either W3 or it selects a 1. And this is the full-blown implementation using only multiplexers. As you can see, this is exactly the same that they've drawn here. They've just connected those two and connected those two. Nice, yes? Okay, so in the next lecture, we'll be looking at combinational building blocks. So now we were looking at decoders, which implicitly also mean encoders, and we'll be looking at some priority encoders. Then we'll also be looking at the lag and the latency that comes with some of these gates, because obviously when you toggle an input, the output doesn't change immediately. It takes a few nanoseconds or a few microseconds to change. So we'll be looking at timing as well. Thanks.